As we continue looking at classifying reactions, the next type that we're going to look at are called displacement reactions or replacement reactions, depending on who you talk to. Our book calls them displacement reactions, so that's what we'll go with. But essentially, in a single displacement reaction, what happens is elements are trading places. So to recognize a single displacement reaction, we're looking for a reaction in which one element takes the place of another in a compound. So in order for this to happen, it requires that the individual element that is trying to join the compound or replace the like element in the compound be more reactive. So it might look something like this. If compound AX is mixed with element B, and B is more reactive than element A, then B is going to take its place, and so B ends up in the compound with X, and A gets kicked out. I kind of use the Cinderella sort of thing to help make sense out of this. Can you imagine if the prince is at the ball dancing with one of the stepsisters, and Cinderella walks in the room? So we have the prince and the stepsister dancing together, and Cinderella enters the room. Well, of course, in that story, the prince is going to end up dancing with Cinderella, and the poor stepsister is going to be left out in the cold. So that's what is happening during a single displacement reaction. And it only happens when this element that's on its own is more reactive than the element that it is trying to replace. So if we look at this, we can see copper chloride is reacting with aluminum, and aluminum must be more reactive than the copper because aluminum ends up in a solution or in a compound with chlorine, and the copper gets kicked out. And that reaction actually does take place, and it looks something like this. We have the copper chloride solution, and we add the aluminum to it. The aluminum replaces some of the copper, and the copper then settles to the bottom of the beaker. And even in the picture, you can start to see that the copper pieces have started to build up down here on the bottom of the beaker. To decide if the reaction is going to take place or not, we need a series like this. It's called a reactivity series. And what it shows us is in order from most reactive to least reactive, many of the metals. So our general rule then is that in order for the reaction to occur, the single element that's trying to join must be more reactive, therefore higher on this reactivity series, than the element that it's trying to replace. So if we look, our last example had aluminum attempting to replace copper. Because aluminum is higher on the reactivity series, that means it is more reactive, and therefore the reaction would take place as we saw in the picture. The chlorine would be attracted to the aluminum and would leave the copper. A similar type of reaction is called a double displacement reaction or double replacement reaction. And what happens here is a reaction in which two compounds switch their partners. So the ions are exchanged. So we say the double displacement reaction is a reaction in which a gas, a solid precipitate, or a molecular compound forms from the apparent exchange of atoms or ions between two compounds. Double displacement reactions often result in a solid precipitate. It is very, very frequent that we will see that. But what matters the most is that we understand that the two compounds are switching partners. So it might look something like this. AX plus BY switches partners, and A ends up with Y, and B ends up with X. In the Cinderella story, I always think this is a happier story because in the Cinderella story, Although the prince is dancing with the stepsister, he must spot Cinderella dancing with somebody else, let's say a duke. Well, the prince is still going to end up with Cinderella when they switch partners, but now a happier story for the stepsister. She will be dancing with the duke. So we see this in lead nitrate and potassium chromate. The polyatomic nitrate here with the lead ends up switching to be with the potassium, and the polyatomic chromate here, CrO4, ends up combining with the lead. So they truly have switched partners. And if we do this reaction, two clear liquids end up making this yellow solid that will settle to the bottom. And so this is clearly a double displacement reaction that produces a precipitate. When reactions take place, clearly it is the electrons that are involved. And the changes, the switches that are occurring is because the valence electrons are going to form new bonds. Just like when we looked at covalent and ionic bonding being involved, involving the valence electrons, those valence electrons are still involved, and we still do switching and swapping based on electrons. And when we do look at electrons in a chemical reaction, there are some reactions that are taking place that cause actual electron switching, where an atom or an ion has gained electrons, or another atom or ion has lost electrons. We call them oxidation reduction reactions. Sometimes they're called redox reactions. Anytime there is a chemical change in which one of the species, so one of the elements, is losing electrons, we say it is oxidized. And when the other species that it is combining with is gaining electrons, we say it is reduced. Now, for me, it is very, very hard to remember that losing is oxidized and gaining is reduced, because gaining doesn't seem like any kind of reduction to me. Those words don't seem to make sense together. So I learned this with a phrase, Leo says ger. The letters L-E-O are the Leo part, and the letters G-E-R is the ger part. So L-E-O, Leo, losing electrons is oxidation. G-E-R, ger, gaining electrons is reduction. And for me, that is very helpful in remembering what has happened. So substances that accept electrons are reduced. And of course, by gaining electrons, it reduces the positive charge. So that's where the reduce part comes from. And if a substance gives up electrons, it is said to be oxidized. So how do we figure this out? Well, as we go from what an element is like on the left-hand side as a reactant to what that same element is on the product side, we will have to look at the charges. Now remember that when we had ionic compounds, the first element was always the positive. So in this compound, our copper is a positive ion. But over here on the product side, the copper is independent. It is by itself, and therefore it is neutral. So it has gone from a positive charge to no charge at all, which means it has reduced its charge. And to reduce its charge, it would have to gain electrons. So gaining electrons is reduction. If we look at the hydrogen as neutral on the reactant side, because it's an independent element, and then we look at it in a compound on the product side, It's positive on the product side because it's starting out the formula. It's the positive ion. So it has gone from positive, or neutral, excuse me, to positive with the addition of oxygen. So we would say that it has been oxidized. To become positive, though, is to lose electrons, and losing electrons, Leo, is oxidation. We can look at the same thing here. Iron goes from positive to neutral, so it has been reduced. Gaining electrons is reduction, and H2 going from neutral to the positive in the water, its charge has gone from neutral to positive, so that means losing electrons, and losing electrons, Leo, is oxidation. So one more example of this, when the sodium and chlorine combine to form sodium chloride, sodium goes from neutral to positive, which is losing electrons, Leo. Loss of electrons is oxidation. Chlorine has gone from neutral to a negative ion. To become negative means that it has gained electrons. Gaining electrons, is reduction. So chlorine is reduced.